In this unit, we will look at how the concept of equilibrium is applied to acids and bases. Our objective is to look at two definitions of acids and bases, the Bronsted-Lowry definition and the Arrhenius definition, and look at specific examples for each of them. Here we see examples of acids found in foods. We have citric acid found in fruit, lipoic acid found in broccoli, and lactic acid found in yogurt. These are just a few of the examples where acid is present in foods. We also see bases in many substances around us, as many cleaners contain a base. We also see bases such as sodium bicarbonate or calcium carbonate present in Tums, Rolaids, or other antacid tablets. Acids and bases have additional properties beyond those that define them as an acid or a base according to either definition. Acids tend to have a sour taste, such as that seen in lemons or vinegar. They can dissolve many metals, and they neutralize bases. A base tends to be bitter, slippery, and has the ability to neutralize acids. And in fact, the reaction between an acid and a base is called a neutralization reaction because it produces a salt or water. Now, the salt may have acidic or basic properties, which we'll explore in the next unit, but the acidity and basicity of that resulting salt is much less than that of the original acid and base solutions. Here we have four acids pictured. We have two binary acids, meaning they contain two elements, HF and HBr, and we have two oxyacids because they're formed from the polyatomic ions of nitrite and nitrate. However, what we see in common in all four of these acids is that they all have a hydrogen present that can be removed, and it's this dissociation or ionization of this hydrogen ion that lends to the acidity of this molecule. An Arrhenius acid is a substance that produces H+ in aqueous solution. Here we show HBr, and we show that it completely dissociates or ionizes into the H+ and Br- ions. We represent this in the chemical reaction by showing a one-direction arrow. This indicates that the reaction goes completely from reactants to products. We show that we have an H+ in solution, but remember we're in aqueous solution and we're not going to see free H+ ions floating around. What we will see are H3O+ ions, which means exactly the same as H+. So this, the H3O+, is what's truly present in the solution. The H+ is just an abbreviation, but they mean exactly the same thing. Remember that we also know that hydrogen has one proton and one electron. When it loses one electron to form H+, all that remains is a single proton. And so we also refer to this H+ as a proton. Here we have an Arrhenius base that shows KOH dissociating into K+ and OH- ions. This also is a strong base, and this is indicated by the presence of a one-direction arrow rather than an equilibrium arrow. Now we can look at the Bronsted-Lowry definitions of acids and bases. We have conjugate acid-base pairs that differ by a single H+. If I look at NH3, which is acting as a base because it's acting as a proton acceptor, I look at its partner, the conjugate acid of that base, and I see it's NH4+ because it has accepted that proton. Now, NH4+ can behave as an acid because it can behave as a proton donor. And together, the NH3 and the NH4+ behave as a conjugate acid-base pair. When I look at the next example of water, in this case, water is acting as an acid. It's acting as a proton donor because it's giving up a proton and becomes OH-. Water and OH- are now a conjugate acid-base pair. Water is also amphoteric and behaves as a base in some cases. It depends on who it's partnered with. Because when we look at defining what's an acid and what's its conjugate base and vice versa, we are looking at it in the context of a chemical reaction. If we look at a reaction, we can go through and define everything as either an acid or a base. The first thing I want to do is look at my HF and see what substance is most similar to that on the product side. And I see I go from HF to F minus. That's going to be one conjugate acid-base pair. And I also see that I have H2O going to H3O plus, and that will be my other conjugate acid-base pair. And so what I want to do is look at HF and F minus and see how it's changing. I see that HF is donating a proton to something else. I'm not worried about where that proton is going. I just know that HF is donating a proton, and we form F minus. So HF is acting as an acid. F minus is now willing to accept a proton, so it's acting as a base. And because they differ from one another by a single proton, a single H plus ion, they make a conjugate acid-base pair. I can look at the same thing when I look at water. Here, water is accepting a proton going from H2O to H3O plus, therefore water is acting as a base. When I look at H3O plus, it's now willing to donate a proton, and so it's behaving as an acid. And together, H2O and H3O plus make a conjugate acid-base pair because they differ by a single proton. We can look at another reaction such as NH3 ammonia plus water in equilibrium with ammonium ion plus hydroxide ion. We can do the same thing that we did on the previous example. We want to identify the pairs. So I have NH3 and NH4 plus, and I have H2O and OH minus. When I look at water in this example, I see that water is donating a proton and becoming OH minus. Therefore, H2O is acting as an acid in this case. OH minus is willing to accept a proton, so it's acting as a base. And together, H2O and OH minus make a conjugate acid-base pair. I can also look at NH3 and NH4 plus. NH3 is willing to accept a proton, which makes it a base. NH4 plus is willing to donate a proton, which makes it an acid. And because NH3 and NH4 plus differ by a single proton, they make a conjugate acid-base pair. Now let's look at an example. What is the conjugate acid of HSO4 minus? The answer is H2SO4. Because it's asking for the conjugate acid of HSO4 minus, it implies that HSO4 is acting as a base. And if it's acting as a base, then it is going to be a proton acceptor. And if HSO4 minus accepts a proton, then it becomes H2SO4. Now, we could also look at the example where HSO4 minus is acting as an acid, and when it acts as an acid, it's going to act as a proton donor. And when it donates a proton, it will go to SO4 2 minus. So we still have a conjugate acid-base pair in HSO4 minus and H2SO4, as well as another conjugate acid-base pair from HSO4 minus to SO4 2 minus. The difference is, are we treating HSO4 minus as a base, or are we treating HSO4 minus as an acid? Next, we will look at pH and Kw. This K value is the same that we looked at in the previous unit.